Autonomous cart-pushing robots have great potential in public service scenarios. However, most existing works treat the problem primarily as a navigation task, overlooking critical requirements for maneuverability and control robustness. As a result, these methods struggle to perform reliably in complex tasks in real-world environments. Humans can fully use the redundant degrees of freedom in their arms to generate flexible push poses and adaptively adjust forces for precise control without relying on explicit dynamic models. Inspired by human operators, we propose a maneuverable planning and adaptive control framework. Our contribution includes a high-performance algorithm and a custom-built mobile manipulation platform for validation. Notably, our method generalizes to all dual-arm mobile robots, not just this specific design. In motion planning level, there are two task requirements. Existing modeling methods fail to fully exploit the dual-arm redundancy, resulting in large turning radii. When handling sharp global paths in cart pushing, this limited maneuverability introduces unnecessary cusp points, causing speed discontinuities, degraded tracking performance, and unsafe planning. Our modeling method fully leverages dual-arm redundancy, significantly improving steering flexibility and enabling smoother global path execution. To reduce the computational complexity caused by redundancy during planning, local coordinate systems are often used to simplify the model. Our proposed model achieves minimal parameterization for the cart-pushing task while fully leveraging the degrees of freedom of both arms. Dual-arm cart pushing is typically modeled as motion planning of two rigid bodies connected by a hitch. Cart steering can be achieved by base rotation alone or enhanced using arm push poses to reduce the turning radius. Existing work explores different coordination strategies between arms and base. Our method fully exploits arm redundancy and is provably the most flexible and efficient even for higher DUF manipulators. Compared to our model, other works overly simplify the system, resulting in reduced flexibility. Another key requirement is switching between push poses. The centered pose offers stable control, while the deflection pose reduces turning radius. An effective pushing strategy should use the deflection pose for maneuverability and return to the centered pose for stability. The requirement for push pose coordination introduces additional task planning. To address the overall task and motion planning, we further design a velocity propagation chain for the LF model and formulate a unified optimization problem to directly optimize the best push pose combinations along with arm and base motions. Our basic TD model enhances flexibility and ensures coordination. The improved LF model further achieves simplicity, flexibility, and coordination. After planning the arm motions, control during execution faces challenges. Joint space PD controllers often lack sufficient torque for steering, and complex disturbances further degrade performance. Excessive PD gains lead to motor oscillations. However, the stiffness issue isn't due to motor limits but to unbalanced torque allocation, excessive in some directions and insufficient in steering. To address this, we design a force projection method to enhance steering stiffness and introduce an adaptive controller to compensate for unmodeled disturbances online. Note that this control strategy can apply to manipulators with varying DUFS. We conduct global path tracking experiments in simulation to evaluate the maneuverability of different local planners. Due to the complex trajectories, other planners show large tracking errors and even unstable behaviors like divergence or abrupt acceleration, while ours performs best. The second experiment tests adaptive control under unknown disturbances. Other controllers fail or lag significantly under heavy loads, while ours maintain stiffness and precision. In contrast, most similar works using joint PD controllers lack sufficient torque, severely affecting trajectory tracking. Other adaptive controllers also show noticeable lag and overshoot. Our controller efficiently allocates limited motor capacity to enhance stiffness in key directions while avoiding unsafe accelerations during sudden loss of force. We further evaluated the full planning and control framework in two challenging real-world navigation tasks: a long, winding transport and a sharp turn in a narrow space. Methods like Schultz's, which rely on dense global sampling and direct execution, often fail in such scenarios. Instead, we use a sparse global planner to generate a coarse global path, which is then tracked using our local planning and control framework. The baselines include a framework consisting of a planner based on Schultz's model with a joint PD controller and Schaus framework. Due to planning and control errors, both baselines fail to complete the tasks, while our framework, featuring the proposed LFMPC and robust adaptive controller, successfully accomplishes them with both robustness and efficiency.
Our proposed framework also enables dynamic obstacle avoidance. In simulation, 3 moving cylindrical obstacles obstruct the robot's global path, and the robot successfully detours around them and returns to the original path. In real-world navigation, our approach similarly avoids static obstacles and dense moving crowds, and navigates long distances through narrow spaces, demonstrating safe and robust performance.
Finally, we conduct robustness testing under extreme conditions, including transport with one arm disabled and maintaining stability under external impacts. Even with a damaged arm, our controller provides sufficient stiffness. Moreover, it resists sudden impacts while remaining compliant during normal operation.
So they get it